well. Dear colleagues, I would like to introduce you Professor Zaytsev, the director of our school, lab head, associate professor of Skoltech, with our interesting lecture. Please welcome Alexey.
Thank you for introducing me, and let's start. Today we'll talk about hallucination detection LLMs, but our journey will begin at a different point, but soon we will reach it, because I think that we need some background to be able to understand what is really going on and does not blindly replicate some approaches introduced in different articles. So let's start with like the problem of sound estimation, what is it and why does it appear, and what kind of things we can do about it. So basically, let us imagine like very simple setting. We have two possible classes of pictures, cats and dogs. We train a neural network, so this neural network would predict if a picture has a dog or a cat. Only two possible training labels. But apparently, the space of figures is much richer. Sometimes you will see pictures of giraffes, for example, and it is clearly some another dimension. Because basically, when we are thinking about a classifier with a neural network, we have a vector of predictions for each possible class label. We have some kind of confidence that this specific class is presented in the picture. For example, if the true label, the label for cat is 1, and we see as the picture like the probability of a cat being 0.9, we can judge that we are pretty confident that we have a cat in the picture. Similarly, if we have a second class with the label 0, then we have some low probability that we see a cat. But what if something else appears? Should we predict something like 0.5, something between cat and dog, or maybe something else? Now we want to say something about uncertainty. This problem is not only of some theoretical importance, like judgment of how uncertain our neural network is about some object. But we can apply this kind of uncertainties in different problems. For example, we have blood tests. This is cycles with these red things, and we try to find out if this test is okay or we should retake it because it was performed in a bad way. By the way, I have a very simple question. Who thinks that the picture on the left is a bad test? Like this obscure low blood picture in the top. And okay, so no one? Yeah, the question is the following. So you have these two cycles, yes? Left one and right one. And this one and this one. I hope you can see it. No, you can see it. Okay. And what do you think? Is a bad test on the left or on the right? Raise your hand if you think that it is on the left. Okay, thank you. And raise your hand if you think that it is on the right. Okay, so all who raised hands are wrong, because both of these examples are some good samples, and specifically image on the left depicts some effect, some like reaction of a blood to some component that says that we have a specific blood type on it. But sometimes we don't see this kind of clear picture, and we need to retake this test. And if we have an uncertainty estimation, and we can say that sometimes this blood test is not okay, then we can do this solely based on uncertainty. Another problem closely tied to uncertainty estimation is active learning. So who knows what is active learning? Okay, not a lot of people. So basically, let's consider the following statement. You have a budget of like B possible queen labels, and you have a set of a sample of n objects, but you don't have the labels for them, and this n is much bigger than B. And there is a very natural question: at what points should we query a label? For example, we have this blood examples, and we can like label only part of them because we need to hire an expert who will say what is good and what is bad. And in this way, we can think that we can optimize the sample according to some criteria, typically trying to maximize the quality of our prediction. So we say that we select some subsample, like this is D, Gn, and we have subsample of size B, Gb, and we want this subsample to be good in terms that we train a model using this dB to obtain y hat, let's call it y hat b, and we want to maximize the quality given the constraint on how many points do we query. And active learning means that we are labeling points one by one. So we start with like very small sample of size b, and then add labels one by one to get the big sample, okay, of moderate size. And basically we can use uncertainty to select these points. Because that if we have some uncertainty estimation for some point, it makes sense to add these points to our sample. Because the model does not know what this point represents, it is uncertain about the prediction of this point, it makes sense to query this point. So we can design a procedure that selects the points we are most uncertain about, forming a sample from these points, and then training a model that would have the maximum quality. And in this way, we can improve the quality of a classifier in a way. Another example that I suppose is maybe most common on the slide is that almost every language model, and I would say every language model, actually hallucinates. It means that sometimes it produces ungrounded responses, and it means that sometimes we need to identify if these responses are grounded or not. So basically, the problem statement is pretty simple, but pretty essential to language modeling. If we have a query and a response produced by a language model, can we say that this response is correct? For example, you have as a query, as a prompt, you have a question, you have a response, and it's kind of maybe what is the capital of China? And the correct answer is Beijing, but maybe some language model can answer, I don't know, Paris. And in this case, we will say it is a hallucination, and we need to somehow estimate what is the probability of this hallucination, what is the probability that there is an error in our prediction. And we will actually cover partly all these problem statements in this presentation, with, okay, hallucination being maybe the last because it incorporates the most complex type of input. So not only complex input like a sequence of words, but also typically a complex output. Also a series of words, and we want to quantify if this series corresponds to the prompt in the right way. Basically, we can say that in the very beginning we have this probability, these uncertainties. And actually it is a pretty strong baseline. So basically this problem, to some extent, we would say that it is solved. So we have an object, we have a neural network, we have a representation, then typically we have a fully connected layer, and after this layer we have probabilities for each class presented in the sample, like used during training. Here we have 5 distinct classes, and we have probabilities associated with each class. And we can say that we have, okay, ground truth, and we can say that the maximum probability somehow estimates how confident we are in the answer. For example, we would have not 0.3 for a catch, but something like 0.9. It would mean that we are very confident that this image is a cat, and our uncertainty would be small. So in this case, we would have this predicted probability, and if you take minus the maximum probability, we would obtain some like raw estimation of uncertainty. So it can be good, but also we have this simple answer. We also have a pretty big challenge that arises in the very beginning when we look at our training data. So if you look at typical examples in our training sample, they somehow correspond to the first 2 pictures on the slide. We can say that it is a dog, it is a cat, and we rarely see something in between. We typically don't have cat dogs or dog cats in our sample with 0.5 and 0.5 probabilities for this object. And it means that basically when we learn a model on top of this, we would have some gap in terms of data. We don't have like information in training sample about how certain or uncertain we are. And this is like the essential issue. And basically one way to deal with it would be to have labeled examples like this on the right, but mainly we don't have access to it, and we need to somehow invent how can we deal with this to make everything work and to make our uncertainty estimation reasonable. What is reasonable and what we can think about when we are thinking about uncertainty? Let's consider two examples for a regression and for a classification. For regression, we can say that, okay, let's look at the picture, yes? On the right top picture, we have like these red points. They are the training data. We have our like regression model, like this dark blue curve, and we can say that the measure of our uncertainty can be represented, for example, as a confidence interval, how big it is. And in this picture, you see that it is pretty reasonable, yes? When we have some point near the training point, like this x that near like some red point, red dot, we would say that our uncertainty is pretty low. But if we go far away from this data, we see that, okay, we now have uncertainties, and we need to represent it this way. So one way about thinking what's uncertainty can be measuring some kind of a distance from a training point and say that if this distance is high, then our uncertainty is high. If the distance is low, then our uncertainty is presumably low, and this is one way to look at it. And you can see that we already have two examples on how we should deal with it. For classification, we also have a pretty natural thing that represents uncertainty. This is actually what we have been discussing in the previous slide, yes? We have a probability of a true object, of a true class, and we can say that suppose we have two classes, and so we can say that if the probability is close to 1, we're very certain that the class label is 1. If the probability is close to 0, then the class label is 0. And if it's some way in between, then we have like something like 0.5, that we are uncertain about the class. And we can see example of this kind of model, of this kind of uncertainty estimation as the picture, yes? We have two classes in our training data, yes, orange points and blue points. We have our model, and it is represented here as the color of area of our plot, and we can see that here we have almost all points that are zeros. For this probability there, here we have ones, and in between we have something 0, like 0.5, and it means that if we are between two classes, we are very uncertain about the outcome. So this is what a uncertainty estimation could look like, and maybe should look like, according to some types of our intuition. Also, it makes sense to understand not only like the total uncertainty, but some different type of uncertainty, because for different problems we require different types. And the most typical way to split uncertainty to two sources is to split it to so-called data uncertainty and model uncertainty. By data uncertainty, we mean that we have noise associated with the data itself. We have noisy observations here, yes, in this right, in this left cloud of points, we have high data uncertainty because the true noise of our observations is high. On the right, contrary, we have very low data uncertainty because noise in our observations is low. And this is something we can introduce. For any model we build, we would have this uncertainty on a prediction. We would have this heteroscedastic noise here. But if we go outside our training data, we can say that we have high model uncertainty, because model never seen what this uncertainty, what the target function should be, and what noise in the function we have. Basically, we lack knowledge, and also if there are some alternative terms for these two types of uncertainty, and it is aleatoric and epistemic uncertainty, and epistemic uncertainty corresponds to the lack of knowledge, and epistemic is some Latin root that corresponds to the meaning it's knowledge, this lack of knowledge of the model for some point, and also aleatoric about the noise that is inherent to the data and that we want to estimate. And basically, when we are, for example, thinking about active learning, it typically makes much more sense to add points in the areas where we have high model uncertainty, because the model uncertainty is something we can reuse. But for data uncertainty, the issue is more complex, because basically, if we add more points, we can estimate this noise more precisely, but the quality would not be improved that much. But if we add even a single point, for example, for x that equals to 0, here in the sample, we can improve the model quality in this area significantly. Also, we can provide a similar example of distribution of certain types for the classification problem. Let us imagine that each dot here is a photo of, again, a cat or a dog, and blue cycles correspond to dogs, and red triangles correspond to cats. And so we train a model, and again, we would have high data uncertainty somewhere in the middle, where we have something that can be referred as a dog or as a cat or something like cat dog. And also we can provide an example of high model uncertainty. Some examples of cats and dogs we don't have in a sample, or we have very small amount of these cats and dogs in our sample. For example, this very fluffy dog on the left and this not that fluffy cat on the right. In this case, we can say that we have high model uncertainty, and we can reduce it if we collect more data in these areas. And let us think how can we approach this problem for a specific model and even derive the exact numerical formulas for estimation of the uncertainty and for split of the uncertainty to like data uncertainty and model uncertainty part. So we have typical training data. Yes, like x's, y's, x's are from RD, y is from R, and we have a very common linear regression model. Yes, we have an assumption that our target is the sum of some function of x plus noise epsilon, and we also assume that our function is a linear product of x's and theta's. And we have like Gaussian assumption about noise, and for example, we can say that we are estimating solving a one-dimensional regression problem like blue points. We construct a model. In this case, it corresponds to this red curve, and it somehow recreates this function, this mapping from the space of x's to the space of y. So our goal is to obtain these coefficients using the training data. Basically, if we assume that we have some prior distribution over functions, over linear functions, and we have no data, very little knowledge, we can say that we are uncertain about the function. So whatever function is, it will work, yes, because we have not seen any data yet. But if we add more data, we again obtain a space of possible functions with probabilities associated to each function. But now they are much more concentrated in specific areas. So all these curves are pretty much similar to each other, yes? But there are some still uncertainty in them, and we can quantify this uncertainty. So let us assume that we have a prior distribution of the parameters, yes? A common Gaussian assumption on what the prior distribution for the parameters are before we have seen any data. Given that the prior distribution, we can write down a posterior distribution that would depend on our likelihood, on our probability to observe this specific data given the parameter values and the prior. Yes, so we just say that we obtain this derivation, this formula, using the famous Bayes formula, and we can do this analytically and say that our posterior distribution, or what kind of parameters are more probable given the data, using in this analytical way. Yes, so we have again a Gaussian distribution with some mean value and some covariance metrics for the parameters. And as you can see, these formulas are pretty close to what you have seen for classic linear regression. Yes, so this mu is very similar to, okay, it's exactly the regularized linear regression formula if you cancel these sigmas here, and S is the covariance matrix we also obtain in a pretty natural way. So this is a covariance matrix of data, X transpose X plus the additional terms that corresponds to the regularization, or in our Bayesian word that corresponds to our prior. And given that, we say that we have this distribution, and if we sample a point from the distribution, we obtain some of these curves. And these curves are pretty much reflect our knowledge about the data. So now we have the posterior distribution for the parameters, and in the same probabilistic way, we can describe our uncertainty. So this distribution is actually our uncertainty about the parameters. Yes, it exactly specifies how big is the covariance, how big is the variance that corresponds to them. Now we can forward this to the predicted distribution for specific y at specific point x. Formulate this integral. Yes, so we multiply the distribution for y given x and theta by a specific posterior distribution, specific density for theta given d, and then we integrate over all possible values of theta. So basically we weight the distribution y given x and theta by the probability to see these parameters given our training sample, given our data theta. And so in this case we can look at this integral, think for maybe 1 hour or even less. Okay, you can put this into DeepSeek and obtain result in 1 minute, and obtain that we again have a Gaussian distribution, and for this Gaussian distribution we again have analytical mean and analytical variance. And the mean value, okay, this is something we are less interested right now, but you can say, okay, it's very similar to the mean value for the linear regression. And for the variance, we also have the formula, and it means that we can estimate how uncertain we are about this sigma at specific point x. You can see that we have a part that related to x that depends on x, like this first term, yes, on the right side of the equal sign. And we have the second part of it that corresponds to this irreducible like data uncertainty. We can't do anything about it. And so in this case, we can obtain analytical formula. Okay, I think that, okay, it's maybe not that easy, and not especially given the time constraints to understand everything, but from what you can see, we have the formula for model uncertainty, analytical one that depends on the training data and on a specific point x, and in this case we estimate sigma, for example, from data, and again obtain the full uncertainty as a sum of model uncertainty and data uncertainty. And we really can see that it is the case if we look at this plot. Yes, so suppose that black points are our training points, and we plot 95% confidence interval given our formula for the posterior predictive distribution for y. And we can see that this predictive interval starts to increase if we move away from the training data. This is very natural thing, and again some estimation of the uncertainty. So, okay, we solved the problem. We can go home. Yes? No. Because actually we are interested in a different model. We are interested in a neural network that would be estimated. This is an uncertainty estimation. Sometimes. So basically we want to have the same thing, but for a deep neural network it can be a large language model, it can be a computer vision model. They are not that popular, but still, okay, the principles would be pretty much the same. And to do this, we can try to derive another principled way to estimate uncertainty for a specific point x, given that we have a set of models or a distribution over the models. So we know what models are more probable, what models are less probable, and so on. So basically, let us repeat the formula we have seen and say that the predicted distribution is the integral of the posterior distribution of y given the concrete parameters that correspond, for example, to a neural network at specific point x times the distribution of parameters given our training data d, then we integrate this over all data, over all possible parameters, values of all the neural networks. And we analytically took this integral when we are talking about linear regression. But if you have a neural network, then it's very hard, okay, I would say impossible to get an analytical expression for it. We need to find some kind of approximation here, and very natural approximation comes from, okay, do we have, no, we don't have this formula, unfortunately. Yeah, we have this actually. We can say that it is very close to some kind of Monte Carlo estimate for this integral, yes? So let us sample theta from the posterior distribution theta given g, and say that our distribution we are interested in and the corresponding uncertainty is the mean value over these distributions for sampled theta k from our overall distribution. We can also say that it is an integral, but this pk being the empirical distribution constructed from k capital different values of theta k. So we can say that we should, and we are using this Monte Carlo estimate, and actually this is what we can do even with neural networks. So basically we train many neural networks, for example, initializing from different seeds. By completing this training, we obtain different models. For each model we obtain this predictive distribution, we average this predictive distribution, and now we have uncertainty estimate. There are some variations here, as you can see, and they provide slightly different ways to think about this. So basically we can say that if we are starting at a different seeds, we obtain these blue points, yes? Each time we end up in some local maximum of our likelihood, or in the local minima of minus likelihood, or some other loss function here, and we can aggregate this to have the estimation of this integral. Also, we can try some different approaches, but I suppose they are not, okay, okay, let's spend a few minutes on them. So one approach being like to find out about the uncertainty about a neighborhood of a specific point, and green points correspond to something in between this optimistic approach when we end up with an ensemble of good models and say that uncertainty can be quantified as the mean value of all this stuff, and the way when we consider the exact sampling from the distribution, because basically when we optimize theta to be in some local maximum, we actually don't obtain the true posterior distribution, but typically it's accurate enough. And I suppose we can skip the slide, but go the slide. So typically when we are talking about ensembles from a common machine learning, we can say that for this ensemble our accuracy is typically higher, yes. Also, when we are thinking about uncertainty, we can obtain it from ensembles as well. One way to say that if we have a distribution for a single model, then the overall uncertainty would be the mean value over all these models. Also, another way to think about uncertainty is to find out how different these distributions are. Because if you have different ensemble members and they provide very different uncertainties, then we again can compute discrepancy and say how big our uncertainty is. Okay, cons are pretty obvious, yes. If we have an ensemble of size k, we have training that is k times more expensive, inference also, storage also, and actually it can be like not that good solution if you are talking about large language models. For large language models, typically, okay, we have a single model of one family. No one can spend enough time and money to train few models. So, what we can do if you want to estimate uncertainty using a simple model? Let's look at it. Basically, we can say that there is a baseline I have been talking about. It is not that bad, and it reflects uncertainty pretty good. So we have some input. It can be an image, it can be a text, and then we have a representation, and suppose we have a classifier in the end that says should be like a word cat, a word times. And we have m classes in total, yes, m plus possible words, for example, in our dictionary. Then we take the maximum of these probabilities and say that our certainty and our confidence are the maximum of these predictive probabilities. Very natural thing, yes? Then we take as uncertainty 1 minus this maximum of the probabilities. So we had certainty, we subtracted it from 1, and we obtained uncertainty, yes? We can also think about uncertainty as the entropy of this distribution. As some of you know, the entropy is some measurements of how chaotic our distribution is and how close it would be to the uniform distribution. So using this formula, like minus pi logarithm pi, we obtain, and summed over all possible classes, here it's m, we obtain the entropy value and corresponding uncertainty estimation. Typically, these two values, the uncertainty obtained using the formula on the left and the uncertainty obtained using the entropy formula, are pretty similar in terms of what we result in the applications. But okay, maybe more principled and more natural way is to use the entropy. Also, we can think about other idea on how should we estimate uncertainty. Not from the model itself, but rather from the distance to the training data. And what does it mean? Let us consider a two-dimensional example with two possible classes. So we again have a classification problem, some orange points, some blue points, and we say that our uncertainty is how distant our new point to this training data. And this is what we have in our Duke model. So for like this yellow areas, we say that the distance between a training point, the closest training point, and the new point is small, and the uncertainty is small. But if we go far away, then we have a bigger uncertainty estimation, like based on this intuition about that if we have some new points that is far away from all other points, we have something like outer distribution example, and it means that for this outer distribution example, our certainty should be pretty high. Also, we can see that different samples don't correspond to this intuition, yes? If you take a different sample, typically with a picture on the left, with low uncertainties, far away from the data. If we don't go away, like if we are not between these two classes. And it means that this Duke model is pretty good at estimating so-called model uncertainty, because it's about the model has not seen the data here yet, and it means that okay, it's not something we can do with. But for ensembles, situation is different, and typical ensembles are not very good at estimating so-called model uncertainty. It can't estimate the lack of knowledge, or at least it is doing it not that good. And formally, we can define this uncertainty in this way if we have not a two-dimensional input, but rather a typical neural network. We have a cat, we apply an encoder to it, and obtain an embedding here. So now we have embedded j theta of x for our object. Let us assume that we have some number of classes, k classes, and we have mean embedding for each class. For example, for cats, it is the vector e1, for dogs it is e3, for bird it is e2. Then we can measure the distance between this embedding of our new image to all other like centers here, yes? And say that our uncertainty is the minimum with respect to all classes, exponential of minus the distance between our new embedding of our new point and embeddings of the centers of classes. So basically we measure how different is the object from the closest class in our data. And if it is far away, it is not that good. Also, you can imagine that we can invent something different if you don't have class labels. You just say that let us have all the training data, train some self-supervised model, then obtain the some number of centers. For example, we can cluster the training data and say that we again can define what our distance would be, and so we can define what our uncertainty can be. And that's it. Also, we can apply a more advanced approach to think about all of this and apply a more probabilistically correct approach in the embedding space, and also think about more reasonable embedding space that we obtain in the end. And to complete these two tasks, we applied two additional heuristics to Duke. The first one being the spectral normalization of the last or a couple of last layers in our neural network. So you say that we regularize the parameters and obtain more reasonable embedding space that has better metric properties. For a classifier on the top of this embedding, we also can replace this dense layer with a Gaussian process regression, Gaussian process classification layer. Then can lead to better sort estimate and better take into account the points we are looking at. So it's not about not only the closest points, but also about other points we have. So basically, if we are applying Duke as it is, okay, we would have like a single point to estimate our uncertainty. Something that we estimate from a single point can be not very reliable. So instead, we are doing this thing. We are saying, okay, we have a new point, or embedding of a new point. We have a single point, and instead of looking at this, we can somehow, in a smart way, average these distances and say how much knowledge about this point we have in neighborhood points. And by doing this, we obtain a better sort estimate. And the principal way to think about this aggregation is called Gaussian process classification. And this is something we can do to obtain a better results. There are a few technical details that we need to know to implement this. So how to exactly apply spectral normalization and how to, yeah, very good. And how to apply this Gaussian process classification in the case when we have a very large sample size. It's called random Fourier features Gaussian process regression. Also, okay. Also, we can think about the problem when everything is applied to language models. We can say that now we have like long generations, and we somehow should aggregate this. And the first naive approach is to think about it as aggregation of entropy. So, if suppose we have some question and some answer. In the answer, you generate tokens one by one. And for each generated token, you have a probability distribution of all words in our dictionary with their probabilities that they occur at the same as this next space. So we have a probability distribution over tokens for each position in the output of a language model. And so if you have a probability distribution, you can calculate the entropy of it and measure the uncertainty that corresponds to this entropy. And then a simple approach would be like this, to look at entropy. But actually, when we are talking about language models, we have another problem. Some words can be semantically pretty close to each other. Basically, they have the same meaning or very close meaning. Basically, a selection of either of this word is okay. In all these cases, we obtain a correct answer. So the idea of this approach, for example, like how to take into account some kind of peculiarities of language model, is to cluster the words that are semantically similar or output generations that are semantically similar and calculate for them the corresponding entropy by uniting everything. And you can see an example here in the bottom of the slide. So we start with sample sim question, like what is the capital of not Great Britain but France, and we have 4 possible answers or 3 possible answers, and you can see the likelihood of them, and everything is okay. We calculate the entropy and we are pretty happy about it. But in the right the entropy calculated using the outputs is something counterintuitive, something that does not reflect how language works. And you need to perform an additional step of uniting semantically similar generations to calculate the entropy. So for example, here it is Paris and London, and the first two are actually the same answer to this question. So we unite them and calculate entropy after union, and it works pretty well. Also, we can think about improving uncertainty for some small sample. So basically, imagine that you have a very big like language model, or not very big, but like something like BERT, and you want to solve a classification problem. In this case, typically for this classification problem, you would have very small sample, but you want to have a reasonable uncertainty estimation. We can do again with a simple heuristic, like taking the maximum of the probability, but can we somehow learn from the data we have? Basically, we again can compare this to some baselines, like the distance from this new point to all other points in the abelian space. But also, we can try to think about more advanced head, which we called it actually our work that's under review now, a similar head to what we have after fine-tuning to some separate classification problem, but that exactly wants to produce uncertainty estimation. And we copy what we already had, but also add updates of the weights that and say that our uncertainty estimation would be not a maximum, but a smooth approximation of the max function, because it would be much easier to train, yes? Because if we have a smooth approximation of maximum, we can propagate the gradients and obtain a better propagation of the gradients and have a better thing. Okay, we actually tried a different way to add this intuition to the loss, and the intuition that this new head should be close to the original head, but in the end we obtained a better uncertainty estimation than a head that appears after fine-tuning of a model. Also, let us discuss a few possible applications on how can we use uncertainty estimation in language modeling. One thing is like improving training process through a reasoning. So suppose you want to have a small language model, but pretty good at some tasks. We have some sample of like questions and the corresponding answers, and we fine-tune using this sample. But typically, we can learn some easy things like knowledge bases, like triplets of knowledge graphs in this way. To make it work better, we actually need to include more information about hard knowledge, about hard questions, about how to reason in this specific case. And to achieve this, we preliminarily label how complex, how hard, and how uncertain to a model a specific example looks like. And given this knowledge, estimated using some uncertainty estimation approach, some uncertainty estimation methods, we see that we have easy, medium, and hard questions. And actually, in addition to supervised fine-tuning using this sample, we, for hard questions, apply reasoning. So we generate reasoning and additional input to our model, and using this, we obtain a better model at a reasonable cost. So if instead, for example, used reasoning for easy and medium questions, we would not see any, see very little improvement if we compare to our approach that we call the pipeline in this table. And also you can see that the token number is much smaller than if you do in the full supervised fine-tuning, or if we provide some kind of ablation, some other alternative ways that don't take into account the complexity of examples. And actually, we can do the similar thing. Okay, it's not our job, but it is an article with a pretty similar idea. We can say that we again fine-tune model with additional reasoning for more complex questions, but also we don't allow to include the most complex questions. So we include like medium hard, like it sounds like a steak names, medium rare examples here, and in this way we improve the quality. And for like a common benchmark, we see some improvement. So we initially had a Qwen3 model of these 4 B parameters. Then we use this intuition about complexity of examples and the requirement to fine-tune only on like complex but not that complex examples. And we obtain Polaris after this fine-tuning. That is much, much better for the specific domain. Like this another like red curve. And it is very close in performance to much bigger models with like more than 200 billion parameters. And also you can see how the distribution of the difficulties of questions change over training. This is the bottom right plot. So basically, how can we measure difficulty? Like in a very simple way. Suppose we have a question and we generate like an answer for this question. Also, you can generate not a single answer, but 8 answers using a similar language model, but for example, tuning the temperature. So it would be pretty diverse. And we can count how often we are right about the answer. Like from 0 from 8, it means that we are never right, to 8 from 8, it means that we are always right. And we see that after training, after the so-called RL training, the distribution of complexities changes, and most questions become easy ones. Someone that we have answers that are right almost all the time. So basically, if you have a certain estimation, you can train your model to be much better and even better than much bigger models for the specific thing. Another application example that's work from our colleagues, it's a usage of uncertainty estimation for adaptive retrieval. So I suppose all of you know what is RAG. Yes, so you have some prompt, you search for some information, add extract information to our prompt, and generate answer using prompt and this additional retrieved information. This is called RAG. Yes? And we can say that sometimes we don't need this additional information and we can be more efficient in this way. So you say that the question is very easy. It's like a question about the capital of some country. A language model typically knows about it. In other situations, we can require more than one document. We need like multiple facts, and we need to extract multiple hard facts from a model to make it work. And in this case, we can say that let's extract k items instead of 1. It would be less efficient. It would cost more. But in the end, we would obtain the right answer because we hope that we had enough and complete information for it. And so we can try to optimize this pipeline by making decisions in which cases we need no additional documents and in which cases we need a lot of additional documents. And how we can select what cases are what. In what cases we need these complex pipelines. And actually, the answer is actually something very close to uncertainty estimation. Basically, if we are still uncertain about our answer, it means that we have not generated enough information, we haven't extracted enough information, and it makes sense to mine more information. And we can compare this setting of the usage of uncertainty estimation compared to other settings that uses different ways for this adaptive retrieval. And we can see, for example, that self-knowledge is the best for uncertainty estimation methods. It means that the model is aware that it does not know something. For other metrics, you can also play and find that sometimes you obtain a Pareto efficient solution in terms of the performance of a model, but also in terms of efficiency. How many queries, how many documents we are extracting. But let's finally move to our last topic about hallucination detection. So basically, this problem should be pretty close to the problem of uncertainty estimation for large language models. But now we have like 2 different types of objects. We have a prompt, we have a response, and we can look at this thing all together to say something about the model. Does it hallucinate or not? And we pretty sure that the models now hallucinate. It can be a simple question as this, like calculate some distances using information provided in the context. It can be much more complex, or it can be questions about something great. All right, basically we can say that typically the problem with hallucinations come from limited knowledge. So we can't include all knowledge about the word in a single language model because it is not that big. Also, it is about limited reasoning. Sometimes model can't reason to provide a good solution, or is not trained good enough to make a long enough chain of thoughts to end up with something reasonable. And also this issue can be related to so-called overconfidence issue. Like model is typically most certain about its answers than it should be. So basically we can plot how model is, how certain is the model and how accurate is the answer. And here we see that, for example, model is certain with like a coefficient like 0.8 and actual accuracy is 0.2. It means that model is terribly wrong about it. So it is overconfident. Maybe it comes from like some kind of supervised fine-tuning, from like the bias that the model should be confident to include to be nicer for humans for the usage as a user interface. But still, we see a lot of hallucinations because of this. So actually, there are many questions we can consider about how we should detect hallucinations. For example, in what setting it should work, and for example, is it possible to train hallucination detector if we have no supervised data, if we have no labels? It's actually a pretty interesting question, because each time we want to train a model, we need to collect label data. And these models appear every day, yes? Each month we see, okay, a new bright language model that appeared, and if you are thinking about some supervised approach to attack hallucinations for them, you need to collect some data set of prompts, to collect answers from this language model, and to label these answers if they are correct or not to mark hallucinations. And sometimes you can do this automatically if it's something like select a number and you can check that number is correct or not. But sometimes, and it is a pretty typical scenario for modern benchmarks for LLMs, the output is also a complex text, and we need a human annotator to make this label data. And so, like training this hallucination detection approaches in supervised way is not that effective. Also, about efficiency one more time. We can say, okay, we can try to do something like ensembles. Yes, we generate multiple responses from a model, somehow aggregate these responses, and do hallucination detection. But again, we have an issue with efficiency, because we have much more expensive generation of the answers, and it's not something we should spend time and money on often. Basically, our desire would be to have that hallucination detection using a single generation of the input with output with little additional cost. Also, sometimes we want to be more specific about problem statement, because sometimes we expect short answers, sometimes we have long answers, sometimes we have short questions, sometimes we have long questions, and sometimes we have additional RAG information, and basically maybe some methods will be more efficient in one setting and sometimes in some other setting. And final question, maybe related with the question 2, is does the model itself know that it knows or does not know something? So let's find out. And so we have two natural baselines that is based on a single model. The first example, the first method, is to invent a prompt that is asking about a specific question, how confident is the model. And this prompt can be pretty simple. If you look at the articles, it can be as simple as, you are given a question, please think about how confident you would be about the answer and with what probability you would give the right answer on on the scale from 0 to 100. And this is something that, okay, OpenAI, for example, uses in their papers. And we can do similar generations of this way, and we can call this model as a judge. But maybe more interesting is to think about what we can extract from what model thinks inside. And this incentive estimation should be like inside this big brain, many layers of a language model. And so we have here many tokens. For each token, we have representations at each head, at each layer, and aggregation of information. Looking at specific heads or specific layers can help us to detect uncertainty, detect hallucination of the examples. Also, okay, as for any other machine learning problem, we have many articles and many methods that try to solve the same problem with kind of limited or good efficiency. Okay, they claim that they are SOTA, but okay, apparently it is not always the case. And for more methods, and you can also look at this LM polygraph library. It's a GitHub published by our colleagues there. Let us start with the less efficient but pretty good in terms of quality approaches. And maybe one thing I should mention is semantic entropy that we discussed before, or just an entropy. So somehow we see how the model is thinking at each step, how certain it is about the generation of the next token, aggregate this information, and this would be some kind of hallucination score. And it can be pretty good, especially if you are doing multiple generations. Also, one way, like similar to the model of the judge approach, is self-check GPT. It means that we measure the consistency between many answers. And so basically what we're doing, it's not that hard, as you can see, yes, on the pipeline. So we have some LLM, we have some question, and we have sample stochastically generated responses, like n of them. Also, we can see how this passage, how initial generation is supported by these generators. A typical way to do this is to use a separate NLI model. Okay, it is a classifier if these two pieces of texts corresponds and convey the same meaning, and it means that if they contradict, it's quite possible that these two different pieces correspond to hallucination. So we aggregate this thing over multiple generations, and we obtain self-check GPT. Maybe the one of the most efficient things. Also, we can look at, okay, maybe we can go further. Okay, so, sorry, not the best slide, I would say. Okay, conversion to PDF from PowerPoint made it suffer, but let me tell you the idea here. The idea is the following. So before that, we are generating something very similar. Yes, so we just say, okay, let's take another temperature and generate many diverse answers. But basically, we can try to generate similar facts that and contradict and so on, and obtain a full. Okay, let me draw it. Okay, I suppose it was a chance for me to draw something on a whiteboard. So we have some additional, maybe pretty complex response that consists of many facts. For example, you can see here at the top of Mount Everest, where the atmosphere pressure is much lower than the sea level, the freezing point of water is as low as -40. So we can try to like generate something synonymous. So this an paraphrasing of initial fact, or you can try to decompose this fact to different facts. For example, one fact would be that at the top of the Mount Everest you have a much lower temperature, and another one being that at the top of the Mount Everest you have a much low like atmospheric pressure, and so on. And then you can go on and obtain many paraphrases and facts like this, and obtain this full tree that we can optimize. Now we can estimate how truthful is each claim we had here. So we have some number associated with each element, each node here. And somehow we try to cover like some neighborhood of this initial statement. And so what we can do next, we can try to look at this as a graphical model. Yes, we have a graph, we have probabilities about the confidence, and given that, using like a simple something close to Bayesian sync to obtain confidence in the very initial sync, and say that it would be our confidence in the very end. And it means that actually when we are thinking about language models, we have much more freedom about when we are thinking about like this ensemble-based approaches. And sometimes we need some kind of reasoning, some kind of exploration that help us understand, do we hallucinate or not? And maybe often the question would be how to make this efficient, how to make this work without a lot of additional generation. So here is the formulas. You can follow the article and find out about this formula more. But we can do it in a simpler way. Using the second idea we mentioned, we can try to look at embeddings, at representation at each layer and each head. So, for example, if we have a typical model like with 30 layers and 30 heads, we have something like 1,000 different representations for each token here, and we can try to aggregate it somehow. For example, a typical way that was popular, a couple of years ago, was to take the last representation, the representation of the last token, and train a supervised model on top of it to detect if the model hallucinated. And we can train this model, so it is a supervised approach. And also we can change some hyperparameters. For example, take embeddings of the last token not from the last layer, but from layer number 28, 24, 20, and so on. And actually, we can see here that it affects the efficiency, and the best layer is, in this case, the layer 28. And also, we can see that this approach remains efficient for two language models and for different topics. But maybe the difference is not that. So this is SAP-LMA, and all other approaches. Actually, they were pretty, in a way, similar to what we have seen before. Like, it is true is something like models judge, so we generate some response based on prompt and see how model answers to it, and that's it. And so we can do even better when we try to think about aggregation over all embeddings that we have in the response. So suppose we have prompt, we have a response, and we have many tokens in our response. The simplest way to aggregate sync is to just take the mean pooling over all embeddings of the response. But it does not work like the best, and the author suggested that we can do a better aggregation that they call attention pooling. So basically, we apply the attention layer here. So we learn a query vector, maybe the query that we can call is it a hallucination, and apply attention layer on top of this embeddings I for I from 1 to G, or for J from 1 to I. So we now have this aggregation, and on top of it we train a logistic regression. You can see that we have a pretty small number of parameters for this pooling, and it turns out to be more powerful than a simple embedding-based logistic regression for the last token. And also you can see another phenomenon here, that actually we don't need to take the last layer in the very end. It's better to take some layer in the middle. And it means that we really need to find something that contains information about how a model thinks about it. And basically it also reflects our intuition that we require some internal states of an LLM to create the most efficient hallucination detection. And we can try to extract this in many other ways, given typical constraints. I will illustrate this with this paper called Holoscope. I suppose it was a spotlight paper in NARIPS 2024. And the idea was actually pretty interesting and almost unsupervised. I hope I would remember to tell you why it is almost unsupervised. So basically, we say that we have embeddings. Let us normalize them, so we subtract the common mean from them, and let us create some eigenvectors from of this matrix of embeddings here, and calculate the distances, the membership scores between some object here and these components. So between the embedding of a specific token and this component here. Now we have tokens that are true and tokens that are hallucinated, and the hypothesis after aggregation. And the hypothesis that they should be different. So we select some threshold and separate one group of tokens from another. And now we have labels for each example. So with our assumption, is it a genuine example or is it a hallucination? After that, we train a logistic regression on top of these embeddings and obtain a hallucination detector. And we can do it. Okay, at this step it is something completely unsupervised. Yes, because we created labels on our own something like self-supervised thing, trained the model and so on. But in addition, we need to select the head that we are applying this procedure to. And basically, the author selected these heads using using the selection procedure that just look at these heads and selects the best one. And in this way, it is kind of supervised selection procedure. But anyway, the results were pretty good and pretty impressive. And we also tried this. It works to some extent. Let me provide another example of what and how we can do it, called loopback lens. It worked even better. In our experience, also pretty recent work. And let us look at the idea and another perspective on where do this knowledge about hallucination lives. So let us calculate so-called lookback ratio. What does it mean? We have a token and all other tokens. Let us calculate attention between this token and all other tokens, and we have tokens from prompt and token from the response. So let us average this attention for prompt and attention to response, and now this loopback ratio is attention from prompt divided by attention from prompt plus attention from response. And we call this our lookback score. They aggregate these things over all labels here, so we have a vector of these things, and we train a binary classifier on top of it. I suppose it's also a logistic regression here, using these lookback scores. And this simple thing works pretty well, and I suppose very close to SOTA in many cases. Okay, we'll skip this thing to go to this one. So we were looking at these approaches, at that approaches, and actually we find out that we have some gap. Basically, for example, if you are talking about self-check GPT, it's pretty accurate, but it is not that efficient in multiple generations for it to work. Other approaches that are based on internal states and on training some aggregation on top of it are pretty good, but still not that good, and they transfer not very well. So if you train a hallucination detector on one sample and then try to transfer to another, it doesn't work well. It means that we don't generate some universal features that will allow us to say is the hallucination or not. So we want to somehow take into account how difficult and as a processing of the input in our language model across multiple heads and multiple layers. We don't want to train something, and we want to keep the number of generations to be 1. And so what we can do? We again can look at the attention matrix or the corresponding set of vectors that corresponds to separate tokens. So this attention matrix is basically the matrix of distances between tokens. If you're talking about a generator type of language model, we can somehow form this matrix by taking this lower diagonal matrix and putting the lower diagonal to the upper sync if you want the full matrix of the distances to be presented. And so we have an attention matrix. And now let us separate tokens, two tokens from prompt and two tokens from response, and calculate the distance between the cloud of tokens that correspond to the prompt and the cloud of tokens that correspond to the response. So now we have these two clouds, and we measure the distance between these 2 point clouds. And it turned out in our experiment that the best distance here was so-called m-top diff, the topological divergence. And maybe you can recall the first lecture on the school by Sergei Barannikov. He actually talked about the same paper, but for some reason didn't include some pictures in it. Here are these pictures, and here's the intuition. So basically we work with the attention matrix and calculate the distance between the prompt and the response. And so it should somehow correspond to hallucinations. And also what interesting, the first thing we find out that for different data sets, the heads that correspond to hallucinations are the same. So we have the same 6 heads that have the biggest differences between distances for normal factual responses and hallucinated responses. And it means that we can use as indicators of hallucination, and this knowledge is shared across many things. And so we have this pretty simple approach that we call TOHA. So we select the optimal set of attention heads by just looking at the biggest difference between the distances for hallucination heads and the normal heads. And in the way, it's enough to have 6 of these heads and aggregate of the distances over all these heads. And when we are going back to our requirements, how fast this thing should be, we see that it is comparable with the inference time. So if we think about something like linear probing or attention pooling probing that we considered before when we were thinking about how we should pool based on the attention mechanism all the representations for tokens in the response, we obtain something pretty fast, but actually not very transferable. For other approaches like self-check GPT, semantic entropy, token-wise entropy, okay, for self-check GPT we need about 20 generations. It means that we increase the inference time 1 order of magnitude. Everything else can work faster, but actually inferior in terms of quality. And if we are looking on the transfer between our dataset and other dataset like COCA and SQUAT and so on, we see that our approach in almost all cases is the best, and we still have a reasonable ROCAUC in the classification problem of detection. Is it a hallucination or not in this way? Also, we can say that if we are doing this, we can not only detect something, but we can pretty easily improve the answers. We can select the best answers according to our hallucination scores. So we are doing something pretty similar to what we did before. We have a language model. For this language model, we generate, for example, 100 responses. And now we hypothesize that some of them can be truthful, can be factual, not hallucination. So how to select the best ones? Let us calculate the hallucination score and select the top ones, those with the lowest hallucination scores. And let us see how we improve overall and for specific type of questions. So if you select some random question among this among this 100 generated answers, we have smaller quality. If we select something greedy, also not very good. But if we are doing the probing right way, we improve a few percents. And also we can see why this improvement occurs. Let us look deeper and separate different questions to the types. For example, because we have 100 answers, we can see how often we answer correctly. For example, we have 2 competing answers when we have 2 or more answers that appear in almost all 100 answers. We have something that is consistently incorrect, with most of the answers being incorrect, most of the responses. And for example, here we have consistently incorrect when all answers, all responses are wrong. And we can see that using this probing-based detection of hallucinations, we significantly improve quality of selection of the best answer in these cases. For example, when we most of the time got incorrect answers. So it's pretty interesting thing, and one of the usage of how we can improve generation of language models using our approach based on hallucination detector. So let us provide some answer that we have in 2025 on how models hallucinate and what we should do with it. The first question is, does the model know that it hallucinates? And the answer is yes. Mostly it knows, at least to some extent. We can identify some internal uncertainties that model lives through when it prepares an answer to you. Regarding the second question, do we need supervised dataset to train a hallucination detector? And I would say that we need a supervised dataset, but it can be pretty small actually. I did not cover it too much, but it's enough to have something like 50 or maybe 100 examples, with 50 of them being truthful, 50 of them being hallucinated. So it's not that good, not that bad. About multiple generations or single generation, I would say that mostly we can obtain a good quality using a single generation, but also we can benefit more if we put more compute in generation, more answers. Also, there are still many problem statements, and the correct answer to what approach you should select depends on how the problem is formulated. Do we have this RAG setting? Do we have short, long talk questions? For example, if you're talking about TOHA, it works good when we have long answers, long responses. But if you have short questions and short responses, it works less reliable, I suppose, because we have a small cloud of points for prompt and for response, and it is not that reliable to estimate the distance. So we are now somewhere in between that I know nothing by Socrates and a typical GPT LM that says that, okay, I'm very knowledgeable and very confident about a wrong answer. So I would like to thank the students that helped me to prepare the slides. I really appreciate their help. And also you can join this list on people who prepare slides and do more interesting stuff. And thank you for listening.
Thank you for your lecture. Actually, I have a question connected to real intelligence, like human brains. Human has the ability of knowing that he knows something. Like you don't remember something, but you know that you know it. It's very interesting because it shows that it is not connected to the remembering of the information. So you have memory about something, and you have another part of your brain that is responsible for knowing that you know it. Maybe it needs to be done like some kind of module that is responsible for knowledge of knowing something in LLMs.
Yes, I suppose we identified this heads. You know exactly when it lives. It's here.
Ah, yeah, sure. It's very interesting, like rhyme in real intelligence.
Yeah, I agree. It's very interesting thought. And I think it's very good that we, as AI researchers, can deep dive into the brain. It's much cheaper than like to have to do something with human brain.
Thank you, Professor, for the lecture. I have two questions. First is rather simple. I do not understand what is the hallucination, how we can define it. Could you please share your?
Okay, it's a very good question, and actually different articles unfortunately give different answers. But basically, we can say, okay, let's consider a few examples here. Okay, we can say that we have some context, we have some question, and the answer is wrong. Very basic definition, but it can be more nuanced for sure. For example, sometimes we can say that we don't have a context, we have a question, we want a model to provide an answer, and in this case we say that it is a hallucination if it contradicts some common knowledge. For example, what is the capital of Poland? So, okay, different articles consider different problem statements. Mostly here I consider it the problem when I have additional context, and this information we want to have an answer about is somewhere in this context. I would say this we can call this a RAG scenario.
Yeah, okay, thank you. So you considered only the case, then the answer of the model contradicts to the facts in the context.
Okay, okay. These articles consider different problem statements, but mostly they consider this one. Yes.
Yeah, okay, thank you. Can you identify the exact moment when the model starts to hallucinate? So, is it something binary, for example?
Okay, it's also a good question, and there are kind of separate problem statement that called identification of so-called hallucination span. So, if you have a set of, for example, you generated at you generated some text, and at some moment we can say this is a hallucination. It's a hallucination starts. For example, we again talking about some country, we're asking about the population of this country, and we have this exact number, and it can be wrong, and if it's wrong, it's a hallucination. And yes, for example, this horoscope was designed for detection of hallucination spans. Not necessarily not horoscope, but this article, and it's a binary classification for each token.
Yeah, thank you. And the last question about the article, when researchers found that there is some heads that are responsible for hallucinations, and if I understood correctly, they tried to delete them, and isn't it deteriorates the quality of the whole model, and can instead of deleting the head, the model be retrained on some hard cases for it to not to hallucinate?
Actually, it is a bit different. We say that we have some heads who know that we have a hallucination, that we have a large difference between prompt and response. And we tried to remove this heads. Actually, it was our article. We tried to remove this heads from a language model, but it actually deteriorated the quality of it. Maybe we need to fine-tune it afterwards, but in this basic scenario, because we didn't have enough resources to retrain or fine-tune the model on large corpus, it does not help. Maybe we should remove some other heads to remove the probability, to decrease the probability of hallucinations. Maybe it makes sense, and thank you again for a good question.
Thank you for lecture. May you repeat, please, interpretation of results at tables 5 and 6?
At what?
Tables 5 and 6. Yes,
okay.
This one.
What we are doing? Okay, thank you for the question. And so what we are doing? We say that we consider 3 best efficient methods. Our methods TOHA, linear probing, and attention pooling probing. We train our model, for example, of RAG. Okay, let's look at top left corner of it. We started with RAG truth QA to train a model or to select heads responsible for hallucinations, and see can we use the same detector for another data set. In this case, it's COCA. If we go to the right, we again train a model or select heads using COCA, and then see how this model performs for another dataset, RAG truth QA. So we try to answer the question: does the detector hallucinate or, excuse me, degrade, or quality decreases if we go from one dataset to another dataset, from one type of hallucinations to another? And for sure, we want the quality to be consistent, to be the same, and we see that for our model TOHA, the ROC values for the classification of hallucination problems is much higher after the transfer than the linear problem and the attention pooling problem.
Okay, and is it correct that this dataset has 3 columns, one context, one question, one context, third it's answer.
For truth, yes.
Yes. And
for COCA and Squad, I should check.
Ah, okay, okay, thank you.
Thank you for the questions.
Thank you for your talk. My question is about uncertainty. We know that LLMs can generate code, and you talked about the uncertainty of LLMs. I'm wondering how different and how complex will be the task of uncertainty of LLMs in code.
I think we can try to replicate these pipelines, and I believe that it should work pretty well. Okay, at least some approaches naturally fit into the framework of detecting of hallucinations in code.
So is it because it all on the token level?
Okay, it can work as a token level. It's okay. I don't see. Okay, to be honest, I don't see any problem. Okay, it's very reasonable methods. Okay, you can try, but to select the best one, I suppose it's something you should check on your own or read some relevant literature that tries to benchmark hallucination detection for the code generation problem.
Thank you.
Thank you.
Okay, thank you, Professor. To confirm my understanding of your presentation on hallucination, so I once fine-tuned a translation model, the Google MT5, to translate between Hausa language and Chinese. So it kept repeating some incorrect word in the translation result. So is this also, does it also fall within your, because the scope of this hallucination, it's a bit tricky and confusing. So does this also fall in the scope of hallucination you're discussing?
Yes, yes. Again, we are looking at these things. We have again embeddings. We can aggregate them and detect hallucinations in this setting as well.
Okay. So you also discussed, I think, 2 methods. I think TOHA and the complexity aware, some fine-tuning.
Yes.
So based on this specific problem, so which of these approach you think it's best to mitigate and resolve this problem?
In general, I would recommend to try TOHA and to try look-back lens. Okay, this is this guy here. Okay. And also you can follow the link, and you can follow the link in our paper as well on TOHA, and there would be a GitHub, and you can download GitHub and run your own approach. We tested them for different language models, so I hope you find something that will be easy to adapt to your specific setting.
Okay, thank you.